Module 6, Lecture A, CNN Fundamentals. By the end of this lecture, you will be able to construct basic CNN architectures using conv2D, max pooling 2D, and dense layers in tf.Keras. Prepare image datasets with tf.data and image preprocessing utilities for CNN training. And train and evaluate a CNN on a small image dataset, interpreting accuracy and loss metrics. Convolution layer basics. Understanding filters and strides. A convolution layer uses a small window called a filter that scans across an image to detect specific patterns. The filter's weights adjust during training so it can recognize features such as edges or textures. As the filter moves, it produces a feature map that shows where these patterns occur in the image. Multiple filters operate in parallel, allowing the layer to capture many different patterns, and the number of filters controls how many distinct features the layer can represent. Stride controls how far a filter moves each time it slides across an image, which changes both the output size and the computation needed. With a stride of 1, the filter moves 1 pixel at a time and captures fine details everywhere. When the stride is increased to 2 or more, the filter skips pixels, producing smaller outputs and reducing computation, but losing some detail. This is similar to zooming out and focusing on broader patterns, such as identifying large plots or crop types in satellite imagery instead of precise field boundaries. In convolutional networks, choosing the number of filters and the stride is key because it controls what patterns the model can learn and how efficiently it learns them. More filters let the network capture a wider variety of features, but also increase computation. A stride of 1 in early layers keeps fine spatial details, while larger strides in deeper layers emphasize broader structures. In effect, you are deciding how many questions the network can ask about an image and how closely it examines each region. Careful choices create models that are both accurate and efficient for real-world tasks. Python code. Understanding filters and strides. Let's break it down. Filters and strides in Python are powerful tools that help us process data efficiently. Filters allow us to select elements based on certain conditions. Strides help us skip elements at regular intervals. We'll go through examples step by step. This script gives a visual explanation of how filters and strides work in convolutional neural networks. It uses TensorFlow to build simple two-dimensional convolution layers, and then shows how they process input data. By comparing the outputs produced with different filters and stride values, it helps you see how these choices change the behavior of the convolution operation. The commented line recommends installing TensorFlow version 2.20.0 to match the needs of the script. This specific version is required because the code depends on its particular features and behavior. Installing it is a setup step to ensure the environment is correctly configured before running the rest of the code. We begin by importing several key modules for our work. The operating system module lets us interact with the system environment, and the random module allows us to generate random numbers for tasks like setting seeds or creating random data. We then import NumPy for efficient numerical computing with arrays and mathematical operations. Finally, we bring in TensorFlow, which we will use to build and train machine learning models, including creating convolutional layers and processing image data. We set a fixed seed value to make random operations produce the same results every time the code runs, which is essential for reproducible machine learning experiments. This involves setting the seed for Python's random module, for NumPy's random number generator, and for TensorFlow's random operations. Using the same seed across these libraries ensures that random numbers, neural network training, and other computations behave consistently between runs. This controlled and predictable randomness makes debugging easier and helps verify that results are reliable. We begin by printing the version of TensorFlow currently in use. This step helps confirm that the correct version is installed and compatible with our work. It's especially important when using features or functions that may behave differently across TensorFlow versions. By checking the version first, we can avoid confusion and ensure our code runs as expected. We begin by creating a small 6x6 grayscale image as a two-dimensional array in NumPy. Almost all the values in this array are 0, except for a central block of 1s that forms a simple pattern. This synthetic image provides a clear example for testing how convolutional filters detect features. We also set the data type to 32-bit floating point to ensure it works smoothly with TensorFlow operations later in the process. To prepare our base image for a two-dimensional convolution layer, we reshape it so it matches the required four-dimensional input format. We add one axis at the beginning to represent the batch size, and another axis at the end to represent the number of channels. This gives the image dimensions of batch size, height, width, and channels. With this reshaping, the convolutional layer can correctly process the image data later in the model. We print the shape of the image tensor to confirm its dimensions before using it in a convolutional layer. This check makes sure the image data is correctly formatted and matches the expected input size. Verifying the shape is important so that the subsequent convolution operations can run properly without errors. We create a vertical edge detection filter using a 3x3 NumPy matrix. Each row of this matrix contains the values -1, +1, and 0, arranged so the negative and positive values line up vertically. This vertical alignment makes the filter respond strongly to vertical edges in an image. We set the data type to float32 to keep it compatible with TensorFlow operations used later in the script. We create a horizontal edge detection filter as a small NumPy array designed to highlight horizontal changes in an image. Its first row is filled with -1s, its second row with +1s, and its third row with 0s. This arrangement responds strongly to horizontal transitions in pixel intensity. The array uses the float32 data type, so it works smoothly with TensorFlow operations. We combine the vertical and horizontal edge detection filters into a single three-dimensional array by stacking them along a new axis. Each filter becomes a separate slice in this array. This stack structure forms a kernel that a convolutional layer can use to detect both vertical and horizontal edges in an image at the same time. We reshape the kernel stack so it matches the input format expected by a two-dimensional convolution layer. To do this, we add a new dimension to the kernel tensor by inserting an extra axis before the last one. This change adjusts the tensor's shape so it is compatible with the layer's requirements and can correctly process the input image. We check the shape of the kernel tensor to confirm it matches the expected dimensions for the convolutional layer. This verification step ensures the kernel is structured correctly before it is used. By doing this, we reduce the risk of errors and make sure the convolution operation will run as intended. We define a two-dimensional convolutional layer in TensorFlow's Keras that uses two filters to learn two different patterns from the input. Each filter is 3x3, so it looks at small local regions of the image at a time. The stride is 1x1, meaning the filters move one pixel at a time for detailed feature extraction. Padding is set to valid, so no extra pixels are added around the image, and the output becomes smaller than the input. We also turn off the bias term, so the layer performs only the pure convolution operation. We define a two-dimensional convolutional layer in TensorFlow's Keras library that uses two filters, so it can learn two distinct patterns from the input. Each filter is 3 by 3, which sets the local region of the image it processes at a time. The stride is 2 by 2, so the filters move 2 pixels at a time, and the output feature maps have lower resolution than the input. Padding is set to valid, meaning no extra pixels are added around the image, and the output is smaller than the original. The layer does not include a bias term, so the convolution output is not shifted by an additional constant. To initialize the convolutional layers, we first run the image tensor through each layer once. This step creates and shapes the internal weights, which start with random values. After this initialization, the layers are ready to receive the custom kernel weights we want to assign. This preparation ensures the layers can correctly perform the convolution operations that follow. We assign the same custom kernel to both convolutional layers, so they share identical predefined filters. This ensures that each layer applies the same edge detection operation during convolution. Keeping the filters consistent is important because it lets us isolate and compare how changing only the stride value affects the output. In other words, any differences we see in the results come from the stride, not from different filters. We now apply a two-dimensional convolution layer with a stride of 1 to the image tensor. Pause briefly. The image is passed through the convolutional layer, and the output is then converted to a NumPy array for easier inspection. Pause briefly. This operation slides the filter across the image one step at a time, computing feature maps. Pause briefly. As a result, it captures detailed patterns and edges present in the original image. In the second convolutional layer, we use a stride of 2, meaning the filter moves 2 steps at a time across the image. This larger stride reduces the resolution and size of the resulting feature map. We then convert the output to a NumPy array to make it easier to work with and analyze. This process lets us see how changing the stride value directly affects the dimensions of the feature map. We examine how the stride in a convolution operation changes the size of the output feature map by printing the output shape for different stride values. With a stride of 1, the output keeps a higher resolution because the filter moves 1 pixel at a time. With a stride of 2, the output shape becomes smaller because the filter skips more input pixels. Comparing these shapes makes it clear that increasing the stride reduces the spatial resolution of the resulting feature map. We start by printing a short message to indicate that we are about to show the feature map produced by the first filter when the convolution uses a stride of 1. This serves as a visual check of how the convolution operation has affected the data. We then extract the corresponding feature map from the convolution layer output by selecting the first item in the batch, all its rows and columns, and the first filter channel. Viewing this feature map helps us see how that specific filter has responded to the input image. We now look at the feature map produced by the first filter when the convolution uses a stride of 2. This larger stride skips more pixels, so the output has lower spatial resolution than the original image. By focusing on the first channel of this feature map, we can clearly see how the chosen stride changes the level of detail and the patterns that the filter detects in the image. The key idea is that using more filters in a convolutional neural network lets the model learn more complex patterns from the input data. In contrast, using larger strides in the convolution reduces the resolution of the output feature map. This can make the model faster because the output is smaller, but it also means losing some fine details from the original image. So, there is a trade-off between capturing detailed information and improving computational efficiency. This script uses TensorFlow to show how filters and stride settings affect convolutional neural networks. It creates a small grayscale image and applies 2 convolutional layers that use edge detection filters, one for vertical edges and one for horizontal edges. The first layer uses a stride of 1 and produces a larger output, while the second uses a stride of 2 and produces a smaller output. By comparing these feature maps, you can see how the filters highlight patterns in the image and how increasing the stride reduces resolution and detail, illustrating the trade-off between capturing fine details and improving computational efficiency. Padding and kernel choices. In a convolutional layer, choosing the kernel size and padding is key to how the network processes an image. The kernel size sets how large a local region the network looks at, with smaller kernels focusing on fine details and larger ones capturing broader structures. Padding controls what happens at the image borders. Without padding, the output becomes smaller, while adding padding, often with zeros, preserves the spatial size and edge information. Together, these choices balance how much detail and context the network retains in its analysis. When configuring convolutional layers, you usually choose between valid padding and same padding. Valid padding does not extend the input, so the output becomes smaller, which helps reduce spatial dimensions and computation. Same padding extends the input so that the output size matches the input, which is useful when stacking many layers and preserving spatial detail, such as in semantic segmentation. The choice between them is a trade-off between keeping detailed spatial information and reducing the size and cost of the computation. In convolutional layers, kernel size and padding strongly affect how the network processes spatial information. Small kernels with same padding are efficient, and when stacked, can approximate a large receptive field while keeping the number of parameters low, which is why many modern models favor them. Larger kernels with valid padding shrink the spatial dimensions and capture broader context, which is useful for analyzing larger structures. By choosing kernel size and padding carefully, you control how much detail is preserved, how quickly spatial dimensions are reduced, and how well the model balances local detail with global structure. Python code, padding, and kernel choices. This script introduces the basics of padding and kernel settings in 2-dimensional convolutional layers. It compares how different convolution configurations change the output. To make this clear, it runs on a small batch of randomly generated images, so you can easily see how the outputs differ under each setting. A line that begins with an exclamation mark is a command used to install TensorFlow version 2.20.0. This is commonly done in environments such as Jupyter Notebooks. The purpose is to make sure that this exact TensorFlow version is available so the code runs correctly. It helps maintain compatibility with the script that follows, which depends on TensorFlow's features and functions. We begin by importing TensorFlow, a powerful library for machine learning and deep learning. This gives us access to a wide range of tools and functions for building and working with neural networks. In this script, we will focus on using TensorFlow to create and manipulate convolutional layers. With TensorFlow in place, we can explore how different convolution settings influence the way images are processed. We use TensorFlow's random module to set a fixed random seed so that any random numbers generated are the same every time the code runs. This makes the results reproducible, which is important for comparing outputs and debugging. By choosing a seed value of 7, we ensure that all random operations behave consistently across runs. This line displays the TensorFlow version currently in use. It helps you quickly verify that your environment is using the correct version. This check is important for compatibility and for making sure your code runs and behaves as expected. We use TensorFlow to create a small batch of random grayscale images with values drawn from a uniform distribution. The resulting tensor has a shape that represents two images, each 8 by 8 pixels, with one channel for grayscale intensity. This compact batch is convenient for testing and experimenting with convolutional operations on a simple, manageable dataset. We print the shape of the input tensor to confirm that our random batch of grayscale images has the correct dimensions. This check is important because it tells us whether the data is organized as expected before it enters the convolutional layers. By verifying the shape, we can better understand how the convolutions will act on the images and how they will change the spatial dimensions as they move through the network. We define a two-dimensional convolutional layer using TensorFlow's Keras library that keeps the output image the same height and width as the input by using same padding. The layer is configured with a single filter, so it produces one output channel. Its filter, or kernel, has a size of 3 by 3, which determines the small region that slides over the image to compute each output value. This setup lets us apply convolution while preserving the original spatial dimensions of the image. We are building a two-dimensional convolutional layer using the Keras tools in TensorFlow. The layer uses valid padding, meaning no extra pixels are added around the input image, so the output feature map becomes smaller than the input. It has a single filter, which acts as one feature detector, and the filter size is 3 by 3. This 3 by 3 filter slides over the image to perform the convolution and extract features without using padding to preserve the original spatial size. We now apply the convolutional layer with same padding to the batch of images. This means the layer processes each image while adding padding around the edges, so the height and width of the output match the input. Keeping the spatial dimensions unchanged lets us directly compare the results and see how different padding strategies influence the final output. We apply a convolutional layer with valid padding to a batch of images, meaning the filters slide over the images without adding extra pixels around the borders. This uses the layer's filters and kernel size to process the input, but does not preserve the original height and width. Because no padding is added, the output feature maps have smaller spatial dimensions than the input images. This code reports the shape of the output tensor after applying a convolutional layer that uses same padding. Pause. Same padding keeps the spatial height and width of the output equal to those of the input. Pause. By printing this shape, we can see how the convolutional layer transforms the data while preserving its overall spatial size. This line prints the shape of the output tensor after a convolutional layer that uses valid padding. Valid padding means no extra border is added around the input, so the convolution reduces the spatial dimensions of the result. By checking this printed shape, we can see exactly how the height and width change when valid padding is applied. We define a two-dimensional convolutional layer in TensorFlow's Keras library to process images using a single filter, so it produces one output channel. The filter has a size of 5 by 5, meaning it examines 5 by 5 regions of the image at a time. We use same padding, which adds zeros around the image, so the output keeps the same height and width as the input. This configuration lets us study how using a larger kernel influences the convolution while preserving the original image dimensions. In this step, we apply a convolutional layer with a larger 5 by 5 kernel to the images, using same padding. This means the convolution operation is performed while keeping the height and width of the output the same as the input. By doing this, we can see how increasing the kernel size changes the features the layer extracts, without altering the overall spatial dimensions of the images. This code checks how a convolutional layer with a large kernel and same padding affects the output. By printing the shape of the resulting tensor, it shows that same padding keeps the spatial dimensions the same as the input. In other words, even with a larger kernel size, the height and width of the feature map are preserved. The printed output shape serves to confirm this behavior. We are calculating how many parameters are in the convolutional layer that uses the smaller kernel size. To do this, we call the layer's countParameters method, which returns the total number of trainable weights in that layer. This value tells us how complex the layer is and how many resources it will require during training. By comparing this number for different kernel sizes, we can better understand the impact of kernel size on the model's overall complexity. In this step, we calculate how many parameters are in a convolutional layer that uses a larger kernel size. We do this by calling the layer's parameter counting method, which returns the total number of trainable weights in that layer. This total shows how the choice of kernel size changes the number of parameters, and therefore the overall complexity of the model. This line of code prints how many parameters are in the convolutional layer that uses a small kernel. Seeing this number makes it clear how kernel size directly changes the total parameters in the model. This helps you understand how choosing different kernel sizes affects model complexity. It also highlights the trade-off between having a more complex model and achieving good performance. This code reports how many parameters are in a convolutional layer that uses a larger kernel size. By comparing this count to smaller kernels, you can see how increasing the kernel size adds more parameters. This demonstrates how kernel size directly affects the complexity of the model. The script ends by printing a brief summary of what the convolution examples showed. It explains that using same padding keeps the output the same height and width as the input, while valid padding makes the output smaller. It also notes that larger kernels require more parameters. Together, these points reinforce how padding choices and kernel size affect both the output shape and the complexity of a convolutional layer. This script uses TensorFlow to show how padding and kernel size affect two-dimensional convolutional layers. It applies convolutions to random grayscale images with two padding options: same padding, which keeps the output height and width the same as the input, and valid padding, which makes the output smaller. It also compares a 3x3 kernel with a larger 5x5 kernel, both using same padding, and shows that the larger kernel increases the number of learnable parameters. Overall, it demonstrates that padding controls output size, while kernel size controls parameter complexity. CNN activation functions. Activation functions are crucial in convolutional neural networks because they introduce nonlinearity, allowing the model to learn complex patterns. After a convolution layer produces feature maps, each value passes through an activation function that decides how important that pattern is for the next layer. Without activation functions, stacking multiple convolution layers would behave like a single linear transformation and could not capture intricate image structures. By acting as a gate on feature importance, activation functions help CNNs progress from detecting simple edges to recognizing complex objects, such as faces or traffic signs. In modern convolutional networks, a common activation function is ReLU, which sets negative values to 0 and keeps positive values unchanged. This simple operation speeds up training and helps prevent the vanishing gradient problem that can slow learning in deep layers. ReLU also leads to sparse activations, where only certain filters respond strongly, making learned features easier to interpret. In medical imaging, for example, this helps the network highlight critical regions in an X-ray by activating only the most relevant filters, supporting more accurate diagnosis. In convolutional networks, the choice of activation function strongly affects learning and feature detection. ReLU is common, but variants like leaky ReLU and parametric ReLU keep a small slope for negative inputs, which helps prevent neurons from becoming inactive. Sigmoid and hyperbolic tangent functions can be useful for tasks such as binary classification, but they may slow training in deep networks. In practice, you apply your chosen activation function after each convolution and dense layer to control information flow and help the network distinguish subtle features, for example, when classifying different plant species. Python code, CNN, activation functions. This material introduces a simple script that demonstrates how activation functions work in convolutional neural networks. It uses small models built with TensorFlow to keep the focus on the behavior of the activation layers rather than on complex architectures. In particular, it compares and illustrates how the ReLU and sigmoid activation functions behave inside these tiny models. The goal is to help you see the practical differences between these two common activation choices in a clear and compact way. The line starting with an exclamation mark is a command to install TensorFlow version 2.20.0, often used in notebook environments to ensure the script runs with the correct version. In this case, the line is commented out, so it does not actually run when the script is executed. This usually means the user expects TensorFlow to already be installed, or simply wants to document the required version. It serves as a reminder of the dependency, without reinstalling it every time the code is run. We begin by importing a few key libraries that set up our environment for machine learning. The operating system library is available for interacting with the system, even though it is not directly used here. We bring in a random number library to generate varied data, and a numerical computing library to efficiently work with arrays and mathematical operations. Finally, we import a deep learning framework that we will use to build and train neural networks. Together, these tools provide the foundation for data manipulation and model creation in our code. To make code produce the same results every time it runs, we set a fixed seed value, such as 42, for all random number generators. This seed initializes the randomness in Python's built-in random module, in NumPy, and in TensorFlow. Using the same seed across these libraries ensures reproducible behavior, which is important for debugging and for fairly comparing experimental results. We begin by printing the TensorFlow version in use, so we can confirm our environment is set up as expected. This step is important because different TensorFlow versions may offer different features or behave differently. Seeing the version number helps us quickly check compatibility with our code and makes debugging easier if something does not work as intended. We begin by generating a small batch of fake image data to work with. The batch contains 4 images, each 8 pixels high and 8 pixels wide, with a single channel to represent grayscale. We use a random number generator to simulate pixel values for these images, then convert the numbers to the float32 format, which is a standard way to store image data in many machine learning tasks. We print the shape of the image batch to quickly confirm that its dimensions are correct before doing any further processing. This check verifies that the batch size, image height, image width, and number of channels match what we expect. By confirming the shape early, we reduce the chance of running into errors in later operations that depend on these dimensions. We build a simple convolutional neural network block using the Keras sequential model to process image data. Inside it, we add a 2-dimensional convolutional layer with 2 filters, each using a 3x3 kernel. The layer uses the ReLU activation function to introduce nonlinearity while remaining efficient to compute. The input shape is set to 8 by 8 by 1, so the model is prepared to handle batches of small grayscale images with those dimensions. We build a simple convolutional neural network using TensorFlow's sequential API with just one convolutional layer. This layer uses two filters of size 3 by 3 and applies the sigmoid activation function. The sigmoid function converts the layer's outputs to values between 0 and 1. The input shape is 8 by 8 by 1, matching our small example images, so we can clearly observe how the sigmoid activation behaves in this basic convolutional setup. We run a forward pass by feeding the batch of images into the convolutional neural network that uses the ReLU activation function. As the images move through the layers, the ReLU function introduces nonlinearity, so the model can learn more complex patterns. The final transformed data produced by this forward pass is stored as the output of the ReLU model. We now run a forward pass through the sigmoid-based model, using the batch of images as input. The images are processed by the convolutional layer, and the sigmoid activation function is applied to its outputs. This produces transformed feature values that represent how the model responds to each image. These processed results are then stored together as the sigmoid output for further use or analysis. The code first prints the shape of the output from the model that uses the ReLU activation to confirm that the data dimensions after this layer are correct. It then prints the shape of the output from the model that uses the sigmoid activation for the same reason. By checking these shapes, we verify that both models handle the input properly and produce outputs with the expected structure. We analyze the ReLU layer by computing basic statistics of its activations. Using TensorFlow, we find the minimum and maximum values of the ReLU output to see the range of activation values, and convert these results to standard floating point numbers for easier use. We also calculate the mean activation value to understand the average level of activity in the layer. Together, these measures describe the overall distribution of ReLU activations. To analyze sigmoid activations, we compute basic statistics over the entire output. We first find the minimum activation value using a TensorFlow function that reduces the data to its smallest value. Then find the maximum value with a similar reduction. We also calculate the mean activation to get the average value across all outputs. Each of these results is then converted to a standard Python float, so they are easier to work with in later processing. We examine the summary statistics of activations from both the ReLU and sigmoid models to compare their behavior. For the ReLU model, we look at the minimum, maximum, and mean activation values to understand its range and average output. We then compute the same statistics for the sigmoid model. By comparing these values, we gain insight into how the two activation functions differ in their output characteristics. To find how many outputs from a ReLU activation are exactly 0, we use TensorFlow's math tools to count the elements in the ReLU result that are equal to 0. This count directly tells us how many activations were turned off by ReLU. We then convert this count to a regular Python integer using a NumPy conversion method and print it. The final number gives us a measure of how sparse the ReLU activation output is. This script uses TensorFlow to compare ReLU and sigmoid activation functions in a simple convolutional neural network. It generates a small batch of random image data, builds two models that share the same architecture but use different activations, and confirms that both produce outputs with the same shape. The script then computes basic statistics of the activations, such as minimum, maximum, and mean values. With ReLU, some outputs are exactly 0 because negative inputs are set to 0, which is counted explicitly. With sigmoid, all activations fall between 0 and 1, illustrating its squashing behavior and providing a clear contrast with ReLU on the same input data. Pooling and flattening. Pooling layer basics. Pooling layers in convolutional networks compress spatial information in feature maps after convolutions detect local patterns like edges or textures. They scan small neighborhoods in each feature map and replace them with a single value, reducing the map's size while keeping the number of channels. Max pooling, the most common type, takes the highest value in each window, preserving the strongest responses. This creates a more compact representation that keeps important features for recognition, while discarding less relevant detail. Pooling layers help neural networks become less sensitive to the exact position of features in an image, focusing instead on whether a feature appears within a region. In tasks like handwritten digit recognition, max pooling treats nearby pixel locations as essentially equivalent and keeps only the strongest response. This idea also applies to medical imaging, where small lesions may shift slightly between scans, but can still be detected within the pooling window. By summarizing local information, pooling layers make models more robust to small shifts and noise, which is important for real-world data that is not perfectly aligned. Pooling layers help control the computational and memory cost of convolutional networks by reducing the size of feature maps as images move through the layers. By downsampling in a predictable way, they speed up training and inference while still preserving important high-level patterns. This reduction in detail also helps limit overfitting, since the model focuses on the most relevant visual cues. Because of this balance between efficiency and sensitivity, pooling layers are a standard component in many architectures used for tasks like traffic sign recognition and satellite image analysis. Python code pooling layer basics. This script introduces the basic idea of pooling in neural networks using TensorFlow. It builds simple layers to show how pooling works and how it reduces the size of feature maps. The script also demonstrates how flattening transforms these pooled outputs into a format suitable for later layers. Overall, it focuses on helping you understand the behavior of pooling and flattening operations. The commented line about installing TensorFlow version 2.20.0 is simply a reminder to use that specific version. This matters because different TensorFlow versions can change how the code behaves, which affects compatibility and reproducibility. Since the line is commented out, it does not actually run as part of the script. Instead, it serves as a note for the user to manually check and install the correct version if needed. In this demonstration, we begin by importing TensorFlow and NumPy, which are the key tools we need. TensorFlow is responsible for building and managing the neural network layers. NumPy supports the numerical calculations and array operations that the network relies on. Together, these libraries provide the foundation for handling the data and computations used throughout the script. We begin by printing the TensorFlow version being used, because this helps ensure that the code behaves consistently across different systems. Knowing the exact version is important for reproducibility, since different releases can change features or introduce new bugs. It also makes debugging easier and allows others to run the same code under the same conditions. In short, checking the TensorFlow version is a simple step that supports reliable and shareable results. We set the random seed for both NumPy and TensorFlow to the same value, 42, so that any random numbers or random operations they perform are repeatable. This means that things like initializing neural network weights will happen in the same way every time the code runs. Using fixed seeds is important when you want deterministic behavior, such as when running experiments or debugging models. We begin by creating a small batch of fake image data in TensorFlow to demonstrate pooling. Using a numerical library, we generate the numbers from 1 to 16 and reshape them into a 4x4 grid with a single channel, which represents a simple grayscale image. This grid is then converted into a TensorFlow constant, so its values stay fixed during computations. With this controlled, unchanging tensor, we can clearly illustrate how pooling operations work on image data. We print the shape of the input batch to confirm that it matches what we expect before continuing. This quick check helps verify that the data is structured correctly and that its dimensions align with the requirements of the model or layer. By doing this early, we can catch mismatches before applying operations such as pooling or flattening. We begin by printing the input values of our image tensor in a clear, readable format. To do this, we reshape the input batch into a 4x4 matrix that represents the image. This simple view lets us see the raw data structure before any processing. By understanding this layout first, it becomes easier to follow how pooling operations will later change the image. In this example, we define a max pooling layer using the Keras tools in TensorFlow. The layer uses a 2x2 window that scans non-overlapping regions of the input. With strides also set to 2x2, the window moves 2 steps at a time horizontally and vertically. This setup cuts the spatial size of the input roughly in half, while keeping the strongest, most important feature from each small region. We now apply max pooling to the input batch using the previously defined max pooling layer. This layer scans the image with a small 2x2 window that moves 2 steps at a time, and for each window, keeps only the largest value. By doing this, it reduces the spatial size of the image while preserving the most important features. The resulting downsampled data is stored as the pooled output. We first check the shape of the pooled output tensor to see the dimensions of the data after max pooling. Then we display the pooled values, rearranged into a 2x2 layout so they are easier to interpret. This shows how max pooling reduces the original image size by keeping only the largest value from each 2x2 region. In this example, an average pooling layer is created using TensorFlow's Keras module with a 2x2 window and a stride of 2x2. This means the layer moves across the input in steps of 2 units in each spatial direction. At each step, it computes the average of the values inside the window. This operation reduces the spatial dimensions of the input while preserving the average feature information, making it useful for downsampling in neural networks. We now apply average pooling to the input batch using the pooling layer defined earlier. This layer moves a 2x2 window across the image and computes the average of the values inside each window. By doing this across the whole image, it reduces the spatial dimensions while keeping the average features of the original input. The result is a smaller output that still represents the main information from the image. We first look at the shape of the average pooled output to see the dimensions of the tensor after average pooling is applied. Then we examine the actual values of this output, rearranged into a simple 2x2 form to make it easier to interpret. Together, these steps show how the average pooling operation changes the original input data into a smaller, averaged representation. In TensorFlow's Keras module, a flattened layer converts multidimensional data, such as the output from a pooling layer, into a one-dimensional array. This step is important because dense layers require a flat input. By flattening the data, we can smoothly pass it from earlier layers into dense layers for further processing in the neural network. After max pooling, the output is passed through a flattened layer, which converts the two-dimensional pooled data into a one-dimensional array. This reshaping step keeps the order of the elements the same, but changes the data's structure. It is usually required before sending the data into a dense layer so the neural network can process it correctly in the next stage. We first print the shape of the flattened tensor to confirm that the original multidimensional data has been correctly converted into a one-dimensional form. This check ensures that the flattening step changed only the structure, not the content. We then print the values of the flattened tensor to see the data in its new linear arrangement and verify that all elements are preserved. Together, these outputs help us understand how the data is being prepared for later stages, such as input to a dense layer in a neural network. This script shows how basic pooling works in TensorFlow using a simple 4x4 image with values from 1 to 16. It first applies max pooling with a 2x2 window, shrinking the image to a 2x2 output by keeping only the largest value in each region. It then applies average pooling with the same window size, producing another reduced image where each value is the average of its region. Finally, the max pooled result is flattened into a one-dimensional array to prepare it for later dense layers in a neural network. Overall, the example illustrates how pooling reduces dimensionality while preserving important features, and how flattening converts the pooled output into a format suitable for further processing. Flatten versus global average pooling 2D. In a convolutional neural network, the final classification stage must convert spatial feature maps into inputs for fully connected layers that produce class probabilities. This can be done either by flattening or by using global average pooling. Flattening takes all the values from the last set of feature maps and arranges them into one long vector, preserving detailed spatial information for the dense layers. In contrast, global average pooling replaces each feature map with a single average value, capturing the overall activation strength of each channel. In simple terms, flattening keeps every spatial detail, while global average pooling summarizes how strongly each feature is present in the image. When choosing between flattening and global average pooling in a neural network, focus on how they affect model size and generalization. Flattening turns feature maps into very high-dimensional vectors, which creates many parameters and can lead to overfitting, especially with limited data. Global average pooling instead compresses each feature map to a single value, greatly reducing parameters and often improving generalization. This works well when the presence of a feature matters more than its exact location, such as detecting zebra stripes in wildlife images. When choosing between flattening and global average pooling, focus on how they handle spatial information and robustness to input changes. Flattening preserves detailed spatial layouts, which helps when you need precise part arrangements, such as telling apart very similar images, but it can make the model more sensitive to shifts or misalignments. Global average pooling instead summarizes each feature map, giving more translation invariance and working better when object position or scale varies, like in user-uploaded photos. Planning which method you will use lets you design datasets and input pipelines that balance spatial detail with model simplicity and robustness. Python code, flatten versus global average pooling 2D. This script demonstrates the difference between using a flattened layer and a two-dimensional global average pooling layer in a convolutional neural network. It builds a very small network and trains it on n-th digit images. The main goal is to show how the dataset is prepared and how these two pooling strategies change the way features from the convolutional layers are passed to the final classifier. This line is a comment that suggests installing TensorFlow version 2.20.0 to match the code's expected environment. Using this specific version helps avoid issues caused by differences in features or syntax between TensorFlow releases. Because the line is commented out it is treated as optional and may indicate that the correct version is already installed. We start by importing 3 key Python libraries. The operating system library lets us interact with the system for tasks like working with files and managing the environment. The random library is used to generate random numbers, which is helpful for things like shuffling data or controlling randomness. Finally, the numerical computing library NumPy allows efficient work with arrays and supports fast mathematical operations. To make our code give the same results every time it runs, we set deterministic seeds for the random number generators. We first set a seed of 42 for the standard random library so that any randomness it produces becomes predictable. We then set the same seed for the NumPy random number generator so that NumPy's random values are also repeatable. Using these seeds ensures our experiments are reproducible, because the random numbers will be identical each time we execute the code. We start by importing TensorFlow, a library used to build and train neural networks. Within TensorFlow, we use Keras as a high-level interface that makes creating deep learning models easier. We also import the layers tools from Keras, which provide components like convolutional, pooling, and dense layers. Together, these imports give us the basic tools needed to define and train neural network models. This command displays the version of TensorFlow that is currently in use. Knowing the exact version helps you check compatibility with your code and libraries. It is also useful for debugging, since different TensorFlow versions can have different features or behaviors. The code first uses a TensorFlow configuration method to list all available physical devices. This step identifies what hardware, such as CPUs or GPUs, is present for running the model. It then prints how many of these devices are found. This gives a quick summary of the computational resources that can be used for training and inference. We begin by loading the MNIST dataset using the datasets module from Keras. MNIST is a standard collection of handwritten digit images used to train and test image processing models. The loading function returns both training and test data, but for this demonstration, we only keep the training portion. We store the training images in one variable and the corresponding digit labels in another, and simply ignore the test data since it is not needed here. For this quick demonstration, we use a smaller subset of the MNIST training data to reduce computation time. We choose 4,000 samples, meaning we only take the first 4,000 images from the training set. We then slice both the training images and their labels to include only these samples. This keeps the features and labels aligned and consistent for any further processing or modeling steps. The code prepares the MNIST training images by first converting their pixel values to 32-bit floating point numbers, then dividing each value by 255 to rescale the range from 0 to 1. This process is called normalization. It keeps all input values on a consistent scale, which helps neural networks train more effectively and with greater numerical stability. The code adds an extra dimension to the MNIST training images, so they can be used with a convolutional neural network. This new dimension represents the image channels. Because the images are grayscale, there is only one channel. Adding this single channel dimension makes the data compatible with the convolutional layers that come next. The code prints the shape of the training subset of the MNIST dataset to verify that the data is correctly prepared for the convolutional neural network. By checking this shape, we confirm that the images have the expected dimensions after pre-processing. This step is important because the later layers in the model rely on receiving data in the correct format in order to process it properly. We create a TensorFlow dataset from the MNIST training data by converting the image and label arrays into a format TensorFlow can process efficiently. This step is important because it allows us to use TensorFlow's data pipeline tools. These tools help manage large datasets and improve the performance of the training process. In short, turning the raw arrays into a TensorFlow dataset is essential for efficient and optimized model training. The dataset is shuffled using a buffer the same size as the subset, so the data is thoroughly mixed. A fixed random seed of 42 is used, so the shuffled order is exactly the same every time the code runs, which ensures reproducibility. This shuffling step is important for effective model training because it prevents the model from picking up accidental patterns from the original ordering of the data. The preprocess function takes an image and its label, resizes the image to 28 by 28 pixels using a TensorFlow image resize operation, and then returns the resized image together with the original label. This resizing step makes sure all images have the same dimensions, which is important for input to a neural network. By keeping the image and label paired, the function prepares the data correctly for the rest of the dataset pipeline. The code uses TensorFlow's data pipeline to apply a preprocessing function to every element in the training dataset. This function resizes each image to 28 by 28 pixels, so that all inputs to the model have a consistent size. The mapping operation is configured to automatically choose how many parallel calls to run based on available system resources. This auto-tuning improves the efficiency of the data pipeline during training. We set the batch size to 64 so that this number of samples is processed together in each pass through the model, which helps with memory use and computational efficiency. The dataset is then grouped into these batches of 64. To further speed up training, we use prefetching so the next batch is prepared while the current one is being processed, reducing idle time. TensorFlow's auto-tuning feature automatically chooses how many batches to prefetch, keeping the input pipeline running smoothly and efficiently. We build a small shared convolutional base by first defining an input layer that matches the 28 by 28 grayscale MNIST images. On this input, we apply a two-dimensional convolutional layer with 16 filters of size 3 by 3, and use the ReLU activation function to add nonlinearity. This convolutional layer allows the model to learn spatial patterns in the images. We then add a max pooling layer with a 2 by 2 window to reduce the spatial dimensions of the feature maps, which lowers computational cost and helps control overfitting by summarizing features in local regions. We add another convolutional layer with 32 small filters and use the ReLU activation function to introduce nonlinearity, allowing the model to capture more complex patterns from the previous layer's output. After this, we apply max pooling with a 2 by 2 window, which reduces the spatial size of the feature maps. This pooling step lowers computational cost and helps control overfitting by summarizing where important features appear in each region of the feature map. To build the classification branch, we first use a flatten layer to convert the convolutional feature maps into a single long vector, since the following dense layer requires a flat input. This vector is then passed to a dense layer with 10 units, one for each possible digit in the MNIST dataset. The dense layer uses the softmax activation function, which turns its outputs into a probability distribution over the 10 classes. This allows the model to estimate how likely each digit is present in the input image, and select the most probable one as its prediction. We first apply global average pooling to the feature maps, which compresses each map into a single value by averaging all its elements and summarizing the spatial information. The resulting set of values is then fed into a dense layer with 10 units that uses a softmax activation. This final layer converts the pooled features into a probability distribution over 10 possible classes. Such an output is well suited for classification tasks with 10 categories, such as digit recognition in the MNIST dataset. We build two separate models that share the same convolutional base, but differ in how they process the feature maps for classification. The first model takes the flattened feature maps as its output and uses them for classification. The second model instead takes the output from a global average pooling layer, which averages each feature map before classification. By constructing both models in this way, we can directly compare how well flatten and global average pooling 2D handle the same underlying features. To train the model that uses a flattened layer, we first configure its training settings. We choose the Atom optimizer because it works well and efficiently updates the model, especially with sparse gradients. For the loss function, we use sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are given as integers. We also track accuracy as the main metric to evaluate how well the model performs during training. This code compiles a model that uses global average pooling and configures it for training. It chooses the Atom optimizer for efficient and adaptable learning. The loss function is sparse categorical cross-entropy, which is appropriate when you have multiple classes and integer labels. During training, the model tracks accuracy as the main performance metric. The model is trained for one pass over the data, using the version that includes the flattened layer, and it uses the training dataset prepared earlier. During this training run, no progress messages or detailed updates are printed. This silent mode is helpful when you only need a quick check of the training process and do not require detailed output. This code trains a model that uses global average pooling for a single epoch on a prepared and batched training dataset. The training runs without printing progress updates. The goal of this brief training run is to compare how global average pooling performs against using a flattened layer, focusing on both accuracy and how efficiently each method uses parameters. We first measure how many parameters the model has when it uses a flattened layer, which tells us about its complexity and memory needs. Then we repeat this process for the model that uses a global average pooling layer. By comparing the parameter counts of these two models, we can see how the choice of pooling strategy affects the overall model size and its potential performance. We determine the final training accuracy of the flattened model by taking the last recorded value from its accuracy history. We do the same for the global average pooling 2D model, using the last value in its accuracy list. Comparing these two final accuracy values lets us directly evaluate which model performed better after training. The code compares how many parameters are in two different models. It first prints the parameter count for the model that uses a flattened layer, then prints the count for the model that uses a global average pooling two-dimensional layer. By looking at these two numbers, you can see how the choice of layer affects the size and complexity of each model. This comparison helps you understand which model might be more efficient or simpler. The code reports the training accuracy of two models so we can compare their performance. It first reads the accuracy of the model that uses a flattened layer from the training history and rounds it to 4 decimal places. It then does the same for the model that uses a global average pooling layer. This makes it easy to quickly see how accurate each model was after training. We first look at the shape of the feature maps to see how their dimensions change after the convolution and pooling layers, which shows how the data is transformed through the network. Then we check the length of the output from the flattened layer to see how these feature maps are turned into a single, one-dimensional array for the following dense layer. Finally, we examine the length of the output from the global average pooling layer to see how it compresses each feature map into a single value, creating a more compact representation of the data. This script compares flatten and global average pooling in a convolutional neural network trained on the MNIST digit dataset. After normalizing and reshaping the images, it builds two models that share the same convolutional layers, but differ in how they convert feature maps into a final representation. One uses flatten to create a long vector, and the other uses global average pooling to compress each feature map to a single value. Both models are trained briefly with the same optimizer, then their parameter counts and training accuracies are compared. The results typically show that the global average pooling model has fewer parameters, can train faster, and may generalize better. And the script also examines the shapes of the feature maps to highlight how the two pooling strategies change the model structure. Managing feature map size. When designing convolutional networks for images, it is important to control how the spatial size of feature maps changes across the model. Choices about convolution, pooling, and stride directly affect these dimensions, which in turn influence memory use, computation, and what patterns the network can learn. If feature maps stay too large, training becomes inefficient, especially for high-resolution images such as medical scans. If they shrink too much, the network may lose critical details needed for tasks like detecting small defects. The key is to balance feature map size so that important information is preserved while keeping the model practical to train and deploy. In convolutional networks, you control the size of feature maps by choosing the input image resolution, setting strides and padding in the convolutions, and deciding where and how much to use pooling. For tasks like handwritten digit recognition, you might keep images smaller and use moderate pooling to preserve fine details. For tasks like aerial image analysis, you might downsample more aggressively to emphasize larger patterns. Overall, you select a target input size and design the convolution and pooling stages so that feature maps are not so large that training becomes slow, but not so small that important structures are lost. To manage feature map sizes in convolutional networks, start by consistently resizing and batching your images, since the initial input dimensions affect every later layer. When using pooling or strided convolutions, choose an input resolution that produces clean, manageable feature map sizes in deeper layers, rather than awkward shapes. This is especially important when your dataset contains images from different sources with varying resolutions. By standardizing image sizes and planning how each layer transforms them, you can train efficiently on your hardware, keep reasonable batch sizes, and still maintain enough spatial detail for the task. Thoughtful control of feature map sizes improves the stability, speed, and accuracy of your convolutional models. Python code managing feature map size. This script demonstrates how to control the size of feature maps in a convolutional neural network. It uses MNIST digit images with simple pre-processing, then applies operations like pooling to reduce spatial dimensions. Finally, it examines the shapes of the data after pooling and after flattening, so you can see how these steps prepare the features for later layers in the network. The line with the exclamation mark is a command that installs TensorFlow version 2.20.0. Specifying this exact version makes sure the script uses the expected library and avoids problems caused by changes in newer or older releases. This practice helps keep machine learning projects consistent and reliable across different environments. We begin by importing several key libraries needed for our work. The operating system library lets us interact with the file system and environment settings, and the random library allows us to generate random numbers, for example, to shuffle data. We then import NumPy for efficient numerical computations with arrays and mathematical operations. Finally, we bring in TensorFlow, which we will use to build and train our convolutional neural network and manage the sizes of its feature maps. We start by setting a seed value, such as 42, so that all random operations are repeatable. We apply this seed to the random library, to NumPy, and to TensorFlow so that each of their random number generators produces the same results every time the code runs. This coordinated seeding makes the behavior of random processes consistent. It is especially important when training machine learning models, because it allows us to reproduce the same results across different runs. This line checks and prints the version of TensorFlow currently in use. It helps you quickly confirm that your environment has the intended version of the library. This is important because using the correct version helps avoid compatibility issues and ensures your code runs as expected. We begin by loading the MNIST dataset using the Keras datasets module in TensorFlow. MNIST is a standard collection of handwritten digit images used to train image processing models. The loading function returns two sets of data, one for training and one for testing, each with images and their labels. For our purposes, we only use the training images and labels so we can focus on managing feature map sizes during the training process. To speed up processing when working with the MNIST training data, we use only a small subset of the dataset. We choose a subset size of 512 samples and keep just the first 512 images and their labels. This reduced dataset makes the code faster to run and easier to test and debug while we develop our methods. To prepare the MNIST training data for a convolutional neural network, we first add a new dimension to represent the single image channel, since these networks expect three-dimensional input. This step changes the data shape so that each image includes a channel dimension. We then convert the data to 32-bit floating point format, which is standard for numerical work in machine learning. This ensures the data is compatible with TensorFlow operations and can be processed efficiently during training. The code prepares the MNIST training images by scaling their pixel values to fall between 0 and 1, done by dividing each original value by 255. This process, called normalization, puts all input values on a consistent scale. Using normalized pixel values generally improves how well machine learning models train and how stable their learning process is. We set the target image size to 28 by 28 pixels to match the original MNIST images. This ensures that any resizing in the pipeline keeps the correct scale and aspect ratio. By doing this, we maintain consistent pre-processing and provide the model with inputs in the expected format. We convert the MNIST training images and labels from NumPy arrays into a TensorFlow dataset using the Data API. This creates a dataset object that TensorFlow can handle efficiently. Doing this is important because it enables streamlined data processing, including applying transformations and batching. As a result, the data pipeline becomes more efficient and easier to manage during model training. We use a pre-processing function that takes an image and its label, then prepares the image for the neural network. It first checks that the image has the expected shape of 28 by 28 pixels with a single channel, ensuring consistency in the data pipeline. It then resizes the image to the same target size of 28 by 28 pixels, so that all inputs are uniform. Finally, the function outputs this processed image together with its original label, ready for the next steps in training or evaluation. The code first pre-processes the dataset by passing each element through a function that fixes the image shape and resizes it to the desired dimensions. This step makes sure all images are consistent and ready for the model. After that, the data is grouped into batches of 32 samples. Batching lets the model handle many images at once, which uses hardware acceleration more effectively and makes training and evaluation more efficient. To understand the shape of our data, we take a single batch from the training dataset and look at the images and labels it contains. We store the images from this batch in a variable, so we can inspect their dimensions. This lets us see how the data looks after preprocessing and batching, which is important for understanding how it will move through the model. By checking this early, we can confirm that the data is correctly prepared for training. We first print the shape of the input batch to see the overall dimensions of all images being processed together, which lets us confirm that the batch size and image size are correct. Then we print the shape of a single image from that batch to verify that each image has the expected height, width, and number of channels. Checking these shapes is important because the convolutional neural network relies on these dimensions being correct for proper processing. We build a small convolutional neural network using a sequential model that takes 28 by 28 grayscale images as input. It first applies a two-dimensional convolutional layer with 8 filters of size 3 by 3, using same padding and a ReLU activation. Then it reduces the spatial size with a 2 by 2 max pooling layer. A second convolutional layer with 16 3 by 3 filters and same padding is added, followed by another 2 by 2 max pooling layer. The resulting feature maps are flattened into a one-dimensional vector and passed to a final dense layer with 10 units and a softmax activation, which outputs class probabilities for the digits 0 through 9. To set up the model's input tensor, we first run a batch of images through the model once. This initial pass is important because it lets TensorFlow determine the input dimensions and build the internal structure it needs. As a result, the computational graph is prepared, and the model is properly configured to process data and extract features in later steps. We build a feature extractor model using the Keras model class that reuses the input from the first layer of our existing convolutional neural network. This model is set up to output the activations from several key stages: the first convolutional layer, the first pooling layer, the second convolutional layer, the second pooling layer, and the flattening layer. By examining these outputs, we can see the shapes of the feature maps at each step and better understand how the data is transformed as it moves through the network. The code runs a batch of images through a feature extractor model and records the intermediate feature maps at key stages. It first saves the output after the initial convolutional layer, then after the first pooling layer. It then captures the output after the second convolutional layer and the second pooling layer. Finally, it records the output after the flattening layer. This lets us see how the feature maps change step by step through the convolutional neural network. We examine the shapes of the feature maps at each key stage of the convolutional neural network to see how the data changes. After the first convolutional layer, we check the shape to understand how convolution affects the input dimensions. We then look at the shape after the first pooling layer, which usually reduces the spatial size, and repeat this process for the second convolutional and pooling layers to observe further transformations and reductions. Finally, we print the shape after flattening, where the multidimensional feature map is converted into a one-dimensional vector for the dense layers. Together, these checks give a clear picture of how the data is progressively transformed through the network. This line of code prints the length of the flattened feature vector produced after the convolutional and pooling layers. At this stage, the feature maps are reshaped into a single one-dimensional vector. The printed value tells you how many features are in that vector, which reveals the size of the data passed into the final dense layer. This helps you understand how much the network has reduced the data's dimensionality before classification or prediction. This script shows how feature map sizes change as data moves through a simple convolutional neural network trained on the MNIST digit dataset. It sets a fixed random seed for reproducibility, loads and normalizes a subset of images, resizes them to 28 by 28 pixels, and organizes them into batches. The network uses two convolutional layers, each followed by max pooling, and ends with a dense layer for classification. At each major step, the script prints the shape of the feature maps, from the initial input batch through each convolution and pooling stage to the final flattened vector. This reveals how the network gradually reduces spatial dimensions while increasing feature depth, making it easier to understand how the data is transformed layer by layer. Building image pipelines. Loading images from directories. When training a convolutional neural network on real-world images, a key first step is efficiently loading those images from disk. Images are usually organized in folders, where each folder name represents a class label, such as cats or dogs. The data pipeline must navigate these folders, associate each image with its correct label, and convert the pixel data into tensors with consistent shapes and types. Setting this up properly is essential for building a flexible training system that supports easy dataset changes, scaling, and a clear connection between stored image files and the model's inputs during both training and evaluation. When loading images from directories for a model, you need to set up the data carefully to get reliable training and evaluation. Make sure all images are resized or cropped to the same resolution so they can be batched consistently. Use a consistent mapping from folder names to numerical labels, so each class, such as pneumonia versus normal, always has a distinct and stable index. Finally, split the images into training, validation, and test sets in a way that avoids data leakage, so your evaluation truly reflects performance on new, unseen data. An effective image pipeline should stream data in batches and use the same setup for both training and evaluation. During training, images are shuffled to improve generalization, but during evaluation, they must be processed in a fixed order to keep accuracy and loss measurements consistent. In areas like medical imaging, a disciplined data loader also ensures consistent pre-processing and keeps validation data separate from training data. This careful design helps guarantee that changes in model performance reflect real learning rather than mistakes in how the data is handled. Python code, loading images from directories. This script demonstrates how to load images from folders using basic TensorFlow image tools. It is designed for beginners, focusing on simple, clear usage rather than complex features. The example keeps the output minimal and uses a very small training setup, so you can quickly see how the process works without heavy computation. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0, ensuring the code uses a specific, compatible version. This is commonly done in environments like Jupyter Notebooks. In this case, the line is commented out, so it serves as a suggestion or reminder rather than an active command. Including it helps keep different setups consistent by clearly indicating which TensorFlow version the code expects. We start by importing the operating system library so we can work with files and directories on the computer. We also import the path handling module, which lets us manage file paths in a more intuitive, object-oriented way. Finally, we bring in the random number module, which we can use to generate random values for tasks, such as shuffling data or controlling randomness with a fixed seed. We begin by importing TensorFlow, a main library used for machine learning and deep learning. Within TensorFlow, we use Keras as a high-level interface that makes it easier to build and train neural networks. We also import the layers component from Keras, which provides the basic building blocks for creating these models. Together, these imports prepare the environment for efficiently constructing and managing deep learning models. We begin by setting the random seed to a fixed value, such as 42, so that any random operations in our code are reproducible. Using the seed function from the random library ensures that the same sequence of random numbers is generated each time the program runs. This consistency is important for debugging and for reliably comparing results across different runs of the code. We set the TensorFlow random seed so that any operation involving randomness gives the same result every time we run the code. This makes our experiments reproducible and ensures consistent outcomes across different runs. It is especially important when debugging or when we need to compare model performance fairly. This command displays the version of TensorFlow that is currently in use. It helps you confirm that TensorFlow is installed correctly and that the version matches what your project requires. The code uses TensorFlow's configuration tools to check whether any GPUs are available on the system. It does this by listing all physical devices of type GPU. This information shows if the system can use GPU acceleration for its computations. Having access to GPUs is especially important in deep learning because it can greatly speed up both training and inference compared to using only CPUs. The code uses TensorFlow's configuration tools to check whether a GPU is available by listing all physical devices of type GPU. It then converts this list into a simple true or false value to see if any GPUs are present. Based on that result, it prints a message indicating either that a GPU is available or that only the CPU will be used. We begin by loading the KIFAR10 dataset using the dataset tools in Keras. KIFAR10 is a standard collection of small images, commonly used to train machine learning models. The loading function returns the images and their corresponding labels, which we store for use in our model. The second part of the return data, the test set, is ignored here because it is not needed for this demonstration. The code displays the shape of the CIFAR10 image dataset to verify its dimensions before any further processing. This check confirms that the data has been loaded correctly and matches what we expect. By doing this early, it becomes easier to debug problems and understand how the dataset is structured for later steps in the workflow. For this quick demonstration, we use only a small portion of the CIFAR10 dataset. Specifically, we select a subset of 60 images, taking just the first 60 samples. Limiting the data in this way reduces the computational cost and makes the process faster to run. This approach is useful when we want to illustrate the method without needing to process the full dataset. The code selects the first 60 labels from the CIFAR10 dataset, so they match the subset of images being used. This ensures that each reduced image has a corresponding label. It then flattens the labels from a two-dimensional structure into a simple one-dimensional list. This flattening step removes the extra dimension, so the labels are easier to handle in later processing. After creating a smaller subset of the CIFAR10 dataset, the code prints the shape of the subset images to verify the result. This check confirms that the slicing worked correctly and that the subset has the intended size and dimensions. By validating the shape at this stage, you help ensure that all later processing steps operate on the correct data structure without unexpected errors. We begin by creating a main folder called CIFAR10 small directory using the pathlib library. This folder will act as the central place where all our image data is organized and stored. Using pathlib makes it easier to work with file paths in a clear way and helps ensure the code runs correctly on different operating systems. The code first checks whether the base directory exists, and if it does, it prepares it for new data by clearing out its contents. It walks through the entire directory tree using a recursive search and examines each item it finds. For every item that is identified as a file, the code deletes it. This process ensures the directory is completely clean before any new files are created or stored there. The code makes sure the base directory is clean by first checking if it already exists, and if so, it goes through its contents in order. For each item, it checks whether it is a subdirectory, and if it is, it then looks at everything inside that subdirectory. Any files found in these subdirectories are deleted. This process removes all existing files while keeping the folder structure intact, so the program can start fresh without leftover data from previous runs. The code makes sure the main folder for saving images exists by creating it if needed. It uses a directory creation method from the path handling library and allows the operation to succeed even if the folder is already there. This prevents errors and ensures there is always a proper place to store image data. By doing this first, it prepares a clean, organized environment for all later image processing steps. We create a list of class names that includes the first three categories from the CIFAR-10 dataset: airplane, automobile, and bird. This list is then used to make separate folders for each class. Organizing the images into these class-specific subdirectories helps keep the data structured and makes it easier to manage and access during training and validation. We set up two main directory paths to organize our image dataset. One path combines the base directory with a training folder name to store all training images in a single, defined location. Another path combines the base directory with a validation folder name to store validation images separately. This separation into training and validation directories is essential in machine learning because it allows us to train the model on one subset of images and evaluate its performance on a different subset. The code first creates a training directory inside the base folder to organize images in a clear structure for later loading and processing. It allows the directory to already exist without causing an error, so the script can continue running smoothly. Then it creates a similar directory for validation images. Separating training and validation data into different folders is important for keeping a clean dataset split and properly evaluating model performance in machine learning workflows. Inside the training directory, we create separate subfolders for each class, such as airplane, automobile, and bird. For each class name, we build a path that combines the training directory with that class name and then create a folder at that location. This ensures that a dedicated directory exists to store images for each class. Organizing the training data into these class-specific folders makes it easier to load and process the data later. In this part of the script, we set up the folder structure for the validation dataset by creating a subfolder for each class. We loop through the list of class names, such as airplane, automobile, and bird, and make a matching subdirectory inside the main validation directory. This structure lets us store validation images in an organized way, grouped by class. As a result, it becomes easier to load, manage, and use these images later during the validation process. We create a list of indices from the CIFAR-10 dataset that correspond only to labels 0, 1, and 2. To do this, we loop through the labels with their positions and keep the positions where the label matches one of these three values. These labels represent the airplane, automobile, and bird classes. As a result, we obtain a subset of the dataset that includes only these three types of images. The code limits the number of images used from each class to a maximum of 10. This keeps the dataset balanced, so no single class dominates. It also helps control the overall dataset size, making it easier to work with. This is especially useful for quick demonstrations or when computing power and memory are limited. The code sets up a dictionary that tracks how many images have been processed for each of the first three classes, starting all their counts at 0. As images are handled, these counts are updated, so the program knows how many examples it has from each class. This helps keep the number of images per class balanced, which is important for training the model effectively. We loop through the selected image indices, and for each one, look up its label from the CFAR10 dataset. If we have already reached the maximum number of images allowed for that class, we skip it. Otherwise, we increase the count for that class. Based on this count, we send the first 7 images of each class to the training set and the remaining ones to the validation set. We then choose the correct directory, obtain the class name from the label, extract the image data, and build the file path in the appropriate class subfolder. Finally, we save the image to that location using a TensorFlow image saving utility. The code prints a summary of how many images have been saved for each class, using a dictionary that tracks the count for every class label. This gives a quick view of how the images are distributed across the different classes. By checking this summary, you can confirm that the correct number of images has been stored in each class directory. We set the image height and width to 32 pixels each to create a standard size for all images. This uniform size ensures that every image is processed consistently by the model. Defining these dimensions prepares the data so the neural network receives inputs in the format it expects. As a result, the model can handle all images in a reliable and comparable way. We create a training dataset by loading images from a directory using a TensorFlow Keras utility that automatically infers class labels from the folder names and represents them as integers. Each image is resized to 32 by 32 pixels, and the data is organized into batches of 8 images for processing. The images are shuffled with a fixed random seed, so the order is mixed but reproducible. This setup produces only a training dataset, with no separate validation split defined at this stage. We create a validation dataset by loading images from a directory using a TensorFlow Keras image loading utility. The labels are automatically inferred from the folder names and returned as integer values. Each image is resized to 32 by 32 pixels and grouped into batches of 8. Shuffling is disabled so the images stay in a fixed order, and a seed is set to make the results reproducible. No validation split is used because this dataset is dedicated entirely to validation. The code improves training speed by using TensorFlow's data auto-tune feature to automatically optimize the data pipeline. It then caches the training dataset so that after the first epoch, the data is stored in memory instead of being repeatedly loaded from disk. After caching, the dataset is prefetched so the next batch is prepared while the current one is being processed. This overlap of data loading and model execution leads to faster, more efficient training. The code speeds up model training by optimizing how the validation data is handled. It caches the validation dataset in memory so it can be accessed more quickly during training. It also uses prefetching to load data in the background while the model is running, so new data is ready when needed. The prefetch buffer size is set to adjust automatically for the best performance. We build a simple convolutional neural network in Keras by first normalizing the input images so pixel values range from 0 to 1, and specifying an input size of 32 by 32 with 3 color channels. We then apply a 2-dimensional convolutional layer with 16 small filters and a ReLU activation, followed by max pooling to downsample the feature maps. A second convolutional layer with 32 filters and another max pooling step further reduces and refines these features. After the convolutional part, we flatten the feature maps into a 1-dimensional vector and pass it through a dense layer with 32 units and ReLU activation to learn higher-level patterns. Finally, an output dense layer with 1 unit per class and a softmax activation produces class probabilities for the input image. The model is now being compiled, which means it is being set up for training. It uses the Atom optimizer, which is well suited for efficiently handling sparse gradients. The loss function is sparse categorical cross-entropy, appropriate for multi-class classification when the labels are given as integers. Accuracy is also tracked as a metric to measure how well the model performs during both training and validation. We train the model using the Keras fit method, providing both the training data and a separate validation set to track performance on unseen examples. The training is run for 3 epochs, so the model passes through the entire training dataset 3 times. The verbose setting is turned off, so no progress messages are printed during training. This quiet configuration is useful for quick demonstrations where detailed training output is not needed. The model is evaluated on the validation data using TensorFlow's evaluation function, which calculates how much error the model makes and how accurate its predictions are. The process is run in silent mode, so no progress messages are shown. The resulting values are saved as the validation loss and the validation accuracy, which summarize the model's performance on data it has not been trained on. The code reports the final validation loss by taking the stored loss value, converting it to a standard number, and rounding it to 4 decimal places for clarity. This rounded value gives a clear, concise measure of how well the model performs on data it has not seen during training. The printed result is labeled as the validation loss, so it is obvious what the number represents. This code prints the model's validation accuracy by displaying a short label followed by the accuracy value. The value is rounded to 4 decimal places, so the result is easier to read and interpret. This keeps the output concise, while still clearly showing how well the model performs on the validation data. This script shows how to load images from directories and train a simple model using TensorFlow. It sets a reproducible environment, checks for a GPU, and uses a small subset of the CIFAR10 dataset with 3 classes: airplanes, automobiles, and birds. The images are organized into training and validation folders, with a limited number of images per class, and then converted into TensorFlow datasets that are optimized with caching and prefetching. A base convolutional neural network is built and briefly trained on this small dataset, and its performance is evaluated by printing the validation loss and accuracy. Overall, it provides a beginner-friendly example of image loading and basic model training in TensorFlow. Image rescaling and augmentation. When working with images in convolutional networks, it is important to rescale pixel values to a consistent range, such as 0 to 1. Raw images often use values from 0 to 255, which can make training harder because the numbers are large and uneven. Rescaling normalizes these values so the network's weights can adjust more effectively, and gradient-based learning becomes more stable, reducing problems like exploding activations. This helps the model focus on meaningful visual patterns instead of arbitrary intensity differences, improving reliability across tasks such as digit recognition and medical image analysis. Image augmentation is a key technique for making models more robust and able to generalize. It works by applying random but realistic changes to images, such as rotations, shifts, zooms, or flips, to mimic variations like different camera angles or lighting. In applications like plant disease detection or retail monitoring, this process exposes the model to controlled variations, so it learns features that stay consistent despite these changes. As a result, the model performs better on new unseen images. When designing rescaling and augmentation for images, match these choices to your specific task and evaluation goals because they directly affect training and validation metrics. Use the same rescaling on both training and validation data, so accuracy and loss measure true performance, and apply augmentation only to the training set, so evaluation stays focused on clean samples. Too much augmentation, such as very strong distortions, can hurt learning, while too little can cause overfitting. By monitoring how accuracy and loss respond to different settings, you can adjust your image pipeline to balance useful variability with stable, meaningful evaluation results. Python code, image rescaling and augmentation. This script demonstrates how to rescale and augment images using TensorFlow. It builds simple data pipelines that apply these transformations. The main goal is to help you see and understand the visual effects of rescaling and augmentation, rather than to perform intensive model training. This command installs TensorFlow version 2.20.0. Using a specific version helps ensure the script runs with the exact features and behavior expected for that release. It is a precaution to prevent errors or incompatibilities that can occur when different TensorFlow versions are used. We begin by importing 3 key Python libraries that support data work in the script. The operating system library lets us interact with files, folders, and the system environment. The random module provides tools for generating random numbers and making random choices, which is useful for tasks like shuffling data. The numerical computing library NumPy allows efficient handling of arrays and fast mathematical operations. Together, these imports provide the basic tools needed for data manipulation and processing. To make our code produce the same results every time it runs, we set a fixed seed value for random number generation. We choose a specific number, such as 42, and use it to initialize Python's built-in random generator as well as NumPy's random generator. Once these seeds are set, any random values created by these tools will be identical on each run. This makes our experiments deterministic, which is important for debugging, checking results, and ensuring reproducibility in numerical computations. We start by importing TensorFlow, a widely used library for machine learning and deep learning. After importing it, we check and print the TensorFlow version in use. Knowing the exact version is important because it affects which features are available and helps ensure compatibility with other tools and code. This simple step helps avoid confusion and errors later in the development process. The code uses a TensorFlow function to list all physical devices of type GPU, allowing it to check whether GPU resources are available. This is important because using a GPU can greatly speed up computations. After checking, the code prints how many GPUs were found, giving quick feedback about the current hardware setup. We begin by loading the MNIST handwritten digit dataset using the Keras tools in TensorFlow. This dataset is widely used for training and testing image recognition models. From the data that is returned, we only keep the training images and their labels. We then print the dimensions of the training images to confirm that the data loaded correctly and to understand its structure before further processing. To speed up processing, we work with a small subset of the training data instead of the full dataset. We choose 8 images by taking the first 8 from the training set. For these images, we also extract their corresponding labels. This keeps the images and labels properly matched, while making further operations faster and easier to manage. We first add a channel dimension to the grayscale images using a function that expands the array dimensions. This is important because many image processing methods and neural networks expect images to include a channel dimension, even if there is only one channel for grayscale. After adding this dimension, we check and print the new shape of the image subset to confirm that the channel has been added correctly. This ensures the data is in the proper format for later processing steps. The code first converts the small subset of images to a float32 data type, so they can be used in precise mathematical operations. Pause briefly. It then normalizes the pixel values by dividing them by 255, which rescales them to lie between 0 and 1. This normalization is a standard step in image processing that can help improve model performance. Pause briefly. Finally, the code prints the minimum and maximum pixel values of the processed images to confirm that the normalization worked correctly. We begin by building a TensorFlow dataset from the rescaled images and their labels using the Data API, which is designed to handle large datasets efficiently. We then group the data into batches of 4 images. Batching is important because it reduces memory usage and speeds up training by allowing the model to process several samples in parallel instead of one at a time. We use a simple augmentation layer in Keras as a sequential model that applies 2 image transformations during training. It randomly flips images horizontally, so the model can recognize objects regardless of left or right orientation. It also applies a small random rotation of up to 10% to introduce more variation. Together, these augmentations simulate different viewing angles and orientations, making the model more robust. We begin by creating an empty list to hold batches of augmented images. Next, we loop over the dataset and take a single batch of images as an example. For this batch, we pass the images through an augmentation layer that applies random horizontal flips and small rotations, with training mode enabled so the transformations are actually used. We add the augmented batch to our list so we can later inspect how the augmentation has changed the images. The code takes the first batch of augmented images and converts it into a NumPy array so it can be processed or analyzed outside of TensorFlow. After this conversion, it prints the shape of the batch. This confirms the dimensions of the augmented images and helps ensure that the augmentation step has preserved the expected structure. This step prints the minimum and maximum pixel values in the augmented batch of images to verify that they still lie between 0 and 1 after the transformations. By checking this range, we confirm that the earlier normalization has been preserved. Maintaining this normalized range is important because it keeps the input to the model consistent and reliable during training or inference. We choose a center index, such as 14, to focus on a specific pixel in the image. We then read the pixel value at this position from the original rescaled image and from the corresponding position in the augmented image batch. By printing and comparing these 2 values, we can see how the augmentation process has changed the pixel at that exact location. This simple check helps us understand the effect of augmentation on individual pixel values. We are building a simple convolutional neural network using the Keras interface in TensorFlow. The model is sequential, taking 28 by 28 grayscale images as input. It first applies a 2-dimensional convolutional layer with 8 small filters and a ReLU activation to extract features. Then uses a 2 by 2 max pooling layer to reduce the spatial size and computation. The result is flattened into a 1-dimensional vector and passed to a final dense layer with 10 units and a softmax activation, which produces class probabilities for the digits 0 through 9. We prepare the model for training by compiling it with specific choices. The optimizer is set to Atom, which is well suited for efficient training, especially when gradients are sparse. The loss function is sparse categorical cross-entropy, which matches multi-class classification tasks where the target labels are integers. We also track accuracy as a metric, so we can monitor how well the model is performing during training. We begin by building a TensorFlow dataset from the rescaled images and their labels, which will serve as the input for training. The dataset is then shuffled, so the model does not learn any patterns based on the original order of the data, using a buffer size that matches the subset and a fixed seed to keep results reproducible. After shuffling, we apply a mapping function that runs the data augmentation layer on each image, so transformations like flips or rotations occur only during training. Throughout this process, the labels are left unchanged to preserve the correct pairing between each image and its label. The code prepares the training data for faster processing by batching and prefetching. It first groups the dataset into batches of 4 images, so the model can process several images at once instead of one by one. Then it uses prefetching to load upcoming batches in the background while training is running. This keeps the data pipeline ready with the next batch, reducing idle time and speeding up training. TensorFlow automatically tunes how many batches to prefetch to balance memory use and performance. The code starts training the model using the prepared dataset pipeline. It calls the model's training function on the augmented training data, which includes the image transformations we defined earlier. The training runs for 2 full passes over the dataset. Progress messages are turned off to keep the console output clean, which is useful for quick tests or when you only care about the final results. We examine the model's training history to find its final performance. From this history, we take the last recorded loss value and the last recorded accuracy value, which represent how the model performed at the end of training. We then round both numbers to 4 decimal places and print them. This provides a clear, concise summary of how well the model learned from the data. This script shows how to rescale and augment images using TensorFlow in a simple machine learning workflow. It loads a small part of the MNIST dataset, normalizes the pixel values, and then applies random horizontal flips and slight rotations while keeping the rescaled range consistent. A basic convolutional neural network with a convolution layer, max pooling, and a dense output layer is built and trained briefly on these augmented images. The script reports training loss and accuracy to illustrate how augmentation can affect model performance, providing a compact example of image preprocessing and augmentation in practice. Batching and shuffling. When training a convolutional neural network on images, you usually do not use the whole dataset at once, but split it into batches and update the model after each batch. Smaller batches lead to more frequent updates and can help the model explore the loss landscape, while larger batches give smoother gradient estimates but require more memory and may generalize less well. Choosing an appropriate batch size is important because it affects training speed, memory usage, and how well the model performs on new data. Shuffling is an essential companion to batching during training, because it randomizes the order of images before each epoch. This prevents the model from picking up patterns from the data sequence that could slow learning or trap it in poor local solutions. By shuffling, each batch becomes a more balanced sample of the dataset, rather than a long run of similar examples. This is especially important in settings like medical imaging, where similar cases may be stored together, since shuffling helps avoid biased learning and misleading performance metrics. Batching, shuffling, and training metrics work together to shape how a model appears to learn. With small, well-shuffled batches, it is normal for loss and accuracy to fluctuate because each mini-batch is a random sample of the data. What matters is the overall trend of decreasing training loss and increasing accuracy, along with validation metrics that improve and then level off. If training loss decreases smoothly, but validation loss becomes noisy or starts to rise, it can indicate overfitting or that the batches are not well represented, possibly due to poor shuffling or imbalanced batches. Python code, batching and shuffling. This script demonstrates the basics of batching and shuffling data for training. It uses a very small subset of the MNIST dataset to keep the example simple and clear. With this data, it trains a compact convolutional neural network. The training runs with logging turned off, so the focus stays on the core ideas of batching and shuffling. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. It is often used in environments like Jupyter Notebooks to make sure that this exact version is available. Doing this helps ensure that the code that follows is compatible with TensorFlow and can run correctly using its expected features and functions. We start by importing 3 key libraries. The operating system library lets us interact with the system for tasks like working with files or environment variables. The random library provides tools to generate random numbers and control randomization, which is important for experiments. Finally, the numerical computing library NumPy gives us efficient support for arrays and fast mathematical operations. We set a seed value of 42 so that our random numbers are reproducible, meaning we get the same results every time we run the code. We first set the seed for Python's built-in random number generator, then set the seed for the random number generator in the numerical library. Using both seeds ensures that all random values are consistent across runs. This is important for experiments, comparisons, and debugging, because it removes variation caused by random number generation. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layers module from Keras so we can quickly add components like convolutional and dense layers. Together, these imports provide the main tools needed to construct and train a neural network efficiently. This line displays the version of TensorFlow currently in use. It provides a quick way to check which version of the library is installed. Knowing the exact version is important because different versions may behave differently. This helps with ensuring compatibility and makes debugging easier. The code first checks whether any graphics processing units are available using TensorFlow's configuration tools. If at least one GPU is found, it chooses the GPU as the device, so computations can run faster. If no GPU is detected, it falls back to using the central processing unit instead. This automatic choice helps the program use the best available hardware for performance. The code prints a message that tells the user whether computations will run on the graphics processor or the central processor. This lets the user know which hardware is being used. Understanding this context is important because performance can differ greatly between running on a GPU and running on a CPU. We begin by loading the MNIST dataset using the dataset tools provided by Keras. This loading step returns 2 pairs of data, one pair for training images and their labels, and another pair for test images and their labels. MNIST is a standard benchmark in machine learning that contains images of handwritten digits. Because of this, it is widely used to demonstrate and evaluate image classification methods. To speed up the demonstration, the dataset size is reduced, so the model trains on 4,000 samples and is tested on 1,000. Using fewer training and test examples makes both training and evaluation run faster. This approach is especially helpful for quick demos or when computing power is limited, while still allowing the main ideas of the model to be shown. To speed up the demonstration, we reduce the size of the training dataset by keeping only the first 4,000 images. We then apply the same slicing to the training labels so they match this smaller set of images. This way, each image still has the correct label and the reduced dataset remains aligned and consistent, while making training faster. To speed up evaluation, we limit the test dataset to 1,000 samples. We keep only the first 1,000 test images and then do the same for the test labels. This way, the images and labels stay correctly matched, while reducing the amount of data the model needs to process. The training data is first converted to a floating point format to improve calculation precision. Then each pixel value is divided by 255, so that all values fall between 0 and 1. This normalization is important for neural networks because it keeps the inputs on a consistent scale, which helps stabilize and speed up training. The same normalization is applied to the test data, so that both training and test sets are processed in the same way. To prepare image data for convolutional layers, we need to add a channel dimension to both the training and test sets. This is done by expanding the shape of each image so it changes from a two-dimensional array to a three-dimensional array with a single channel. We apply this transformation to all training images and then to all test images. After this step, both datasets match the input shape expected by the convolutional neural network. The code prints the shapes of the training and test datasets to confirm that the data has been processed and reshaped correctly. This check ensures that the dimensions match the model's expected input format. By viewing these shapes, we verify that both the training and test data are properly prepared and ready for further processing or model training. In this setup, the batch size is set to 64, meaning that 64 samples from the dataset are processed together in each training pass. The chosen batch size directly influences how quickly training runs. It can also affect how well the model learns patterns from the data and how well it generalizes to new, unseen examples. We begin by turning the training images and their labels into a TensorFlow dataset. This means organizing the raw data into a structure that TensorFlow can process efficiently. Doing this is important because it allows us to use TensorFlow's data pipeline tools, which handle large datasets more effectively. As a result, the training process becomes more streamlined and better optimized. We start by creating a dataset that is batched but not shuffled, meaning we group the training data into fixed-size batches while keeping the original order. The batch size controls how many examples go into each group. Because we do not shuffle, the data is processed exactly in the sequence it appears in the dataset. This can help us examine the natural order of the data, but it is usually not ideal for training models that benefit from randomized input to generalize better. We begin by taking the next batch from the version of the dataset that has not been shuffled, so we can inspect how the labels are distributed. Using an iterator, we retrieve the first batch and then focus on the second element of the batch, which holds the labels. We convert these labels into a NumPy array and print the first 10 values. This lets us see how the labels are ordered in the original, unshuffled data and understand its structure before any randomization is applied. We set the shuffle buffer size equal to the number of training samples so that every example is included when the data is mixed. Then we shuffle the training dataset using TensorFlow's shuffle method with this buffer and a fixed seed, which randomizes the order while keeping it reproducible across runs. This thorough and consistent shuffling is important because it helps the model avoid learning patterns that come only from the original order of the data and leads to more effective training. After shuffling the dataset to mix the classes randomly, we split it into batches. This batching step is important because each batch then contains a diverse set of examples. That diversity helps the model learn more general patterns. As a result, training can converge faster, and the model is more likely to generalize well to new data. We begin by taking the next batch from the shuffled and batched dataset, which gives us a randomly mixed sample of data. This random mixing helps ensure that each batch contains a diverse set of classes. We then print the labels of the first 10 samples in the batch to check how they are distributed. By inspecting these labels, we can confirm that the shuffling has effectively mixed the classes and that the batch is more balanced and representative for training. This code uses TensorFlow's prefetching feature to make training more efficient. With automatic tuning, the data pipeline prepares the next batch while the model is still processing the current one. By overlapping data loading and model computation, it reduces idle time, and can speed up the overall training process. To prepare the test data, we use TensorFlow's data tools to build a dataset from the test images and labels stored in memory. A function converts these arrays into a TensorFlow dataset so they can be handled efficiently. This setup lets us process the test data in batches and is essential for feeding it into the model during evaluation. The test dataset is first divided into batches using a set batch size, so it can be processed in smaller, manageable groups. After batching, it is configured to prefetch using TensorFlow's automatic tuning. Prefetching lets data loading happen in parallel with model training, which reduces the time the model spends waiting for data. Together, batching and prefetching make the overall training process more efficient. We build a simple convolutional neural network in Keras as a sequence of layers for digit classification. It starts with a two-dimensional convolutional layer with 16 filters of size 3 by 3 and ReLU activation, taking 28 by 28 grayscale images as input, followed by a 2 by 2 max pooling layer to reduce spatial size. A second convolutional layer with 32 filters and ReLU activation, followed by another max pooling layer, further extracts and downsamples features. The resulting feature maps are flattened into a one-dimensional vector and passed to a dense layer with 64 units and ReLU activation to learn higher-level patterns. Finally, an output dense layer with 10 units and softmax activation produces probabilities for the 10-digit classes from 0 to 9. Before training, the model is compiled, which means we set up how it will learn and how its performance will be measured. We choose the Atom optimizer so the model's weights can be updated effectively during training. We use sparse categorical cross-entropy as the loss function, which is appropriate when we have multiple classes and the labels are given as integers. Finally, we track accuracy as the main metric to evaluate how well the model performs on both the training and validation data. We train the model using the Keras fit method, giving it the prepared training data with batching and shuffling. We set the number of epochs to 3 so the model passes through the entire training set 3 times. For validation, we supply the test data so the model can check its performance on unseen examples after each epoch. The verbose setting is turned off, so training runs without printing progress, which is convenient for quick experiments where detailed logs are not needed. To evaluate how well a model has learned from the training data, we look at the final training loss and accuracy stored in its history. We obtain the final loss by taking the last recorded loss value, which corresponds to the end of the last training epoch. In the same way, we take the last recorded accuracy value to get the model's final training accuracy. Together, these two metrics summarize the model's performance on the training data after training is complete. We look at the final validation loss from the training history to see how well the model fits unseen data at the end of training. We also check the final validation accuracy, which tells us the percentage of correct predictions on the validation set. Together, these two metrics summarize how well the model is likely to generalize to new data. We summarize the model's performance by printing 4 final metrics, each rounded to 4 decimal places for clarity. The training loss shows how well the model fits the training data, and the training accuracy shows the percentage of correct predictions on that data. The validation loss indicates how well the model generalizes to new unseen data, and the validation accuracy shows its prediction quality on the validation set. Together, these values provide a quick, clear assessment of the model's overall effectiveness. This script shows how batching and shuffling work using a small subset of the MNIST dataset. It sets a seed for reproducibility, normalizes and reshapes the images for a convolutional neural network, then creates two batch datasets, one with shuffling and one without, and compares their first few labels to illustrate the effect of shuffling. A simple convolutional neural network is defined, compiled with the atom optimizer and sparse categorical cross-entropy loss, and trained for 3 epochs. At the end, the script reports the final training and validation loss and accuracy to summarize how well the model performed. In this lecture, you learn to construct basic CNN architectures using conv2D, max pooling 2D, and dense layers in tf.Keras. Prepare image datasets with tf.data and image preprocessing utilities for CNN training. And train and evaluate a CNN on a small image dataset, interpreting accuracy and loss metrics. In the next lecture, Lecture B, we will go over transfer learning.
Thank you for your attention. See you all in the next lecture.